Welcome to lecture 6 in week 5 of machine learning foundations. In this lecture we will move on to a topic that is a logical continuation of what we have learned so far, which is we will use spectral theorem. We saw spectral theorem in the previous lecture, which states that any real symmetric matrix is orthogonally diagonalizable. But here we will look at a more general class of matrices which are not necessarily even square. It could be a rectangular matrix, and we will show that every rectangular matrix, say m rows and n columns, can be decomposed using two orthogonal matrices and diagonal matrix, and this is the so-called SVD form, which is the singular, which is short form for singular value decomposition. We will show this decomposition holds for any rectangular matrix. The proof along the way will use the spectral theorem at some point. Okay, before getting into singular value decomposition, I will do a quick recap of spectral theorem, which was covered in a previous lecture video. So, spectral theorem in particular for a real symmetric case. Okay, so we have seen the more general version of this, but let's just recap this. Suppose A is a n cross n real symmetric matrix. Then A is orthogonally, okay, let me put this, then let's put it like this. Then the first claim is all eigenvalues of A are real. Moreover, A is orthogonally diagonalizable. So what do I mean by this? That is, there exists a orthogonal matrix. This is not a standard term, but so Q. This is equivalent to saying Q transpose Q equals identity, such that A can be written as Q transpose, or let's put it more like this. So then you have a diagonal matrix into the transpose. So this is x1 transpose, x2 transpose, and so on until xn transpose. So here these are the eigenvalues of A, and these xi are the eigenvectors of A. Okay, so that's a spectral theorem for you. Just to reinforce the same idea, we'll just do an example where I won't do all the calculations. This is fairly straightforward, just a 2 cross 2 matrix. 1 minus 2 minus 2 minus 2. So what are the eigenvalues? You can find out. I would recommend pausing the lecture video and working out this Q matrix and the eigenvalues on your own. So the eigenvalues turn out to be minus 3 and 2. So let me write it as lambda 1 is minus 3, lambda 2 equals 2. The corresponding eigenvectors are x1 is 1, 2, x2 is minus 2, 1. Now, the normalized versions There are just two eigenvectors, so it's you don't have to take the pain of doing a Gram-Schmidt orthonormalization. Just normalizing, just dividing it by the length will do. So you have 1 by square root 5 and 2 by square root 5, and Q2 equals minus 2 by square root 5 and 1 by square root 5. Once you have this, how do you make up the Q matrix? You take this Q1, Q2. I mean, for you it would be interesting to check Q transpose Q is identity. So when you're working out calculating such things, easy sanity check is to do this Q transpose Q and ensure it turns out to be the identity. If it does not turn out to be the identity, then there is something that has gone wrong in your calculation. You may have to revisit that. In this case, you can check this, and now you can also check Q lambda Q transpose equals 1 by square root 5 2 by square root 5 minus 2 by square root 5 1 by square root 5 into the eigenvalues minus 3 2 whole thing into this turns out to be, this product turns out to be, again check this. Okay, so far what we have seen is this is the story for real symmetric matrices. Now we'll see a more general decomposition. So this spectral theorem or the eigen decomposition is only possible for real symmetric matrices. It's not only possible, there are other matrices which satisfy, but a real symmetric matrix is guaranteed to have such a decomposition. Now the next topic we're going to look at is singular value decomposition, which applies to any matrix even if it is rectangular. We focus on the real case here. So every matrix cannot be diagonalized. Seen enough examples. However, any, I'll put this in quotes, real M cross N matrix, even if it is rectangular, A can be decomposed in the SVD form. So what is the SVD form? That is, A can be written as A equals, so here you have Q1 sigma Q2 transpose. Now if you look at this, Q1 is a M cross M matrix. So get the dimensions right. A is M cross N, Q is M cross M, and Q2 is N cross N. Okay. The other facts are in the respective dimensions. Q1, Q2 are orthogonal. So Q1, Q2 are orthogonal. That is, Q1 transpose Q1 equals identity. Q2 is also equals identity. But this is identity. This is again M cross M, but this is a different identity matrix. This is N cross N. Okay. And the last thing is this matrix sigma has a particular form where D is a diagonal matrix with positive entries
sigma r, where sigma I is greater than 0. Okay, so before delving deeper into this decomposition, let's try to show that, given any real matrix, why does this decomposition even hold? We'll try to argue that any real matrix can be broken up into three matrix product like this, or decomposed into three matrices like this. So, why does, let's call this star, what is the decomposition? Star hold for any m cross n So here is the proof. So here is where we will invoke the spectral theorem at some point. But I would say just think about this decomposition again. Understand that this is a much more general decomposition than the one given by spectral theorem, simply because we are not imposing symmetry here. A could be any matrix. And moreover, we don't even require A to be a square matrix. Any m cross n matrix will do. Okay, so let's understand why this decomposition can be done for any matrix. Formal proof of that. So what is A? A is m cross n. So A transpose A is n cross n. And what kind of a matrix is A transpose A? For any matrix, it does not matter what the matrix A is. For any given matrix, A transpose A is symmetric. By definition, A is having only real entries. So when you do A transpose A, you will still remain with the real entries only. You won't get complex values. So given this fact, implies there exists a basis of orthonormal eigenvectors, let's say x1 until xn, corresponding to, A transpose A can be diagonalized. So that just means that I get enough eigenvectors, and the number of eigenvectors A transpose A is n cross n, so I get n eigenvectors, linearly independent one, and I can also make them orthonormal ones. So we have orthonormal, we have an orthonormal basis for Rn corresponding to the eigenvalues, let's say now here is where we'll start analyzing. So we have, so what do we have? A transpose A is the matrix that we diagonalized. Xi is its eigenvector. So A transpose A, when acted, when you multiply A transpose A with Xi, then you will recover lambda I times Xi for I equals 1 until n. Moreover, these Xi's are orthonormal, so the length of Xi is 1. And Xi dot Xj, in this case, it's just these are eigenvectors, is 0 for all I not equal to j. For all I got, so this is an orthonormal basis. So each eigenvector is of length 1, and they're orthogonal to each other. Yeah. So continuing further along this, so what we have is, if I take A transpose A xi and dot product with xi, this is lambda I xi dot product with xi, and that is just lambda I, since okay. Now I can compute this dot product in a different way also. A transpose A xi dot product with xi is A transpose A xi transpose xi, which is the same as xi transpose A transpose A xi, which is the same as A xi transpose A xi, which is the same as finally. And this is a non-negative quantity. Just by definition, that's the length of a vector AXI. So it's non-negative. So what we have is, using, let me call this equation 1, equation 2, 1 and 2 imply, so this dot product is equal to lambda I, and this dot product is also non-negative, so lambda I has to be non-negative. Okay. Now, if you understand, we said that when we do the SVD, you get a diagonal matrix with some numbers, sigma i's, some r of them. So where are these coming from? And that's where we are going at. So far we have got, so what we have is, let's order the lambdas. So order the eigenvalues of A transpose A, which is like saying that say lambda 1 is the biggest, lambda 2, so on until lambda r, then lambda r plus 1 until lambda n. What we have is, lambda 1 greater than 0, so on until lambda r greater than 0, and all the remaining eigenvalues are equal to 0. Now you make up the definition. So sigma i's are called singular values. Yeah, sigma i's are singular values, called singular values, for each I equals 1 to r, sigma I equals square root lambda I. Okay. So this is for the first, you take the positive eigenvalues of A transpose A. We just say that there are r of them, and if there are r of them, then take lambda 1 until lambda r, take their square root and denote them by lambda I. There's a particular reason why we have to take the square root, because finally that goes into the diagonal matrix. Okay. So we have defined many bits, at least the diagonal matrix is now clear. So the matrix, they call it sigma, right? Yeah. Sigma is now clear. So we know what goes into sigma. Now let's see what goes into Q1 and Q2. But for that we need to do a little more analysis. So let yi equals 1 by sigma I A xi for I equals 1 dot r. So let's just understand some basics here. Xi is a n-dimensional vector. A is a m cross n matrix. So yi belongs to Rm. So it's a m-dimensional vector. Okay. Now what is the length of yi? We know that sigma is positive, so 1 by sigma comes outside. This is length of axi, but this length of axi is the same as lambda. So it's square root lambda I divided by sigma I, but sigma is by definition lambda, so the length of yi's are 1. Each y is of length 1. So axi by definition is lambda xi, and then you know the length. Yeah, it's pretty clear. Yeah. Not axi, I'm really sorry. A transpose axi is lambda xi, but from the calculation here that we have seen, okay, y. Okay, let's see. Because from 1 and 2, non exi square equals lambda I. Yeah. So if you just go up here, we just calculated that lambda I turns out to be the same as axi square. Okay, so that's yi. We'll also show that, if you take yi dot product with yj, I not equal to j, this is going to be 1 by sigma I, sigma j, axi dot product with axj. Now this is the same as 1 by sigma j, and the basic rules of dot product xi transpose a transpose a xj. But a transpose a xj is a eigenvalue of eigenvector of a transpose a. So this is equal to 1 by sigma I sigma j xi transpose lambda j xj, simply because a transpose a xj equals lambda j xj. So this whole thing is equal to lambda j divided by sigma I sigma j into xi transpose xj, but xi transpose xj is just 0, since x1 to xn is an orthonormal basis. Xi transpose xj equals 0 for I not equal to j. So what we have is, we have a set y1 until yr. We have a set of orthonormal vectors. This is not a basis because yi's are in Rm, and we may have r maybe less than m. Okay. Yeah. Since r is less than or equal to m, the set y1 to ym, yr is not a basis. However, we could extend y1 to yr to form a orthonormal basis of Rm. So I need m vectors. So I could add the remaining m minus r vectors. So let us denote that extended set y1 until ym be the orthonormal basis obtained by extending y1 to yr. Now I am ready to define q1. So q1 is going to be, I am going to take these vectors y1 until ym, and in q2 I am going to put the eigenvectors of A transpose E. Okay. So all components of SVD are defined. Now what we need to check, check if A is Q1 sigma Q2 transpose. So with this definition of Q1, Q2, can I recover A, and sigma, can I recover A by this product? Yeah. Okay. So what is sigma? Sigma is Q1 transpose EQ2. Let's do this. Let's see if sigma has the form that we want. So what is Q1 transpose? It's just Y1 transpose until Ym transpose into A times Q2 is just AX1 until AXN. Now if I can show that sigma has this form, if this product Q1 transpose EQ2 has the form where it has a bunch of diagonal entries sigma 1 until sigma r and then zeros elsewhere, then I am done, and that's the last bit of the proof remaining. So this is the ijth entry. So the ijth entry of this product Q1 transpose EQ2 is, I'm going to take yi and multiply it with AXJ. Now let's understand this. Now there are two cases here. The very first case is J less than equal to R. See, the thing about yi says, if you recall, until R, yi has a particular form. So yi equals 1 by sigma AXI for all I less than or equal to R. And beyond R, I got these vectors by extending to a full basis. So let's calculate this for J less than equal to R. So in this case, with J less than equal to R, for J less than equal to R, y J equals 1 by sigma J into AXJ. So what happens to this product? Yi transpose AXJ equals yi transpose. So AXJ is nothing but sigma J yj. So this is equal to sigma J yi transpose yj, and this finally is equal to the two things. It can be equal to sigma j if I equals j and 0 else. Now the second case. So I hope this was clear. Now the case where j greater than r. Now in this particular case, what we have is j greater than r. Observe that what is axj is nothing but lambda j. But lambda j for all j greater than r is just 0. You have lambda r plus 1 until lambda n 0 by definition, which just means axj equals 0. Okay, which finally implies yi transpose axj also equal to 0. Okay, so that covers the entire deal. So what we have is, so the final thing is, so the form we get for sigma is you have sigma 1 until sigma r. Okay, let me put 4 parts here. Okay, and then you have 0 elsewhere. Okay. So this is the diagonal matrix that I was talking about. So this is a R cross R diagonal matrix. So what we have shown is Q1 transpose A Q2 turns out to be this matrix sigma, which is equivalent to saying you just pre-multiply by Q1 and post-multiply by Q2 transpose, and what you will get is Q1 sigma Q2 transpose equals A, and this is the SVD of A. So we've just shown that any M cross N matrix can be decomposed into this particular form, where Q1 transpose sigma into a product, into a product of two orthogonal matrices with a diagonal matrix thrown in. But these two orthogonal matrices live in two different spaces. One of them is M cross M, the other is an N cross N matrix. And also we have seen that Q2 contains, by definition when we saw Q2, what did Q2 contain? Q2 contained the eigenvectors of A transpose A. Now what does Q1 contain? That's a question we'll answer next. I would say just think about this decomposition. Just make a remark about what goes into Q1 and Q2 just from the decomposition. If you had not seen this proof, we can infer what goes into Q1 and Q2. Okay. So A is Q1 sigma Q2 transpose. So A into A transpose is Q1 sigma transpose Q1 transpose. And what you got is this is the eigen decomposition of E into A transpose. So what goes into, so the eigen vectors of E into A transpose go into Q1. A transpose, which is a real, just to emphasize the fact that it's a real symmetric matrix. So A into A transpose is a real symmetric matrix. I can make its eigen decomposition using spectral theorem. and sigma into sigma transpose is going to be a diagonal matrix. I mean, it's needless to say. So sigma into sigma transpose is a diagonal matrix, and Q1 is the matrix where all the eigenvectors go. Now, along similar lines, just from the decomposition, you can infer what is A transpose A. This turns out to be Q2 sigma transpose sigma into Q2 transpose. Okay. Implies the eigenvectors of A transpose A go into Q2. Okay, so those are the remarks. We'll do an example now.
A summary of today's lecture before we wrap up. What did we learn today? First, we looked at a simple example where we worked out the eigen decomposition of a real symmetric matrix, which is an illustration of the spectral theorem in action. And next we moved on to a very important topic, which is the singular value decomposition, or SVD in short. We showed that any rectangular matrix, say M cross N matrix, can be decomposed or written as a product of three matrices, two of them orthogonal, the other is diagonal. And these two orthogonal matrices are of different dimensions, and this diagonal matrix is obviously a rectangular matrix. And what goes into the diagonal matrix are what the so-called singular values associated with the original M cross N matrix. Now, this singular value decomposition holds for any M cross N matrix. We don't impose any additional structure, unlike spectral theorem, which required a matrix to be square, real, symmetric, all of that. We don't need any structure. And in the next lecture, we'll look at a simple example which illustrates how to compute the SVD of a given matrix, given rectangular matrix. We'll try to understand this by example in the next lecture.